Welcome to Probability and Statistics. In this lecture video, we're going to talk about Chapter 6.1, Introduction to Normal Distribution. So here in this section, we're going to formally introduce your bell curve shape. All right, what is so-called a normal curve is when your histogram has a symmetric and bell curve shape. All right, so I don't use the word bell shaped curve anymore. I would just use the word normal curve or normal distribution. So a normal distribution is actually a continuous random variable, which is a little bit different than earlier in the lecture video, the discrete random variable, the binomial distribution. Okay, the binomial was discrete. Okay, so now we're going to begin to talk about your continuous random variable. So when this continuous random variable is normally distributed, that means it has a normal probability distribution. If its relative frequency histogram has a normal curve. Alright, so the word normal means bell curve shape. So if we want to make a transition from chapter 3 material and chapter 2 material, what's happening here is given a relative frequency distribution, okay, like this table number 1, where I have heights and the relative frequency, we can graph the histogram. Okay, so the relative frequency here on the L2 over the y-axis is going to be the same thing as your probability. Okay, so the relative frequency actually become probabilities. Okay, from now on. So if the histogram look like a bell curve shape, we have what we so-called normal curve, which we can actually find the areas under the curve. All right. So we are taking our distribution, divide things up into classes, find its relative frequencies. So once I got relative frequency and create my histogram, now my y-axis becomes the probability. All right. If the histogram look like a bell curve shape, then now what we're going to do is begin to talk about the areas under the curve. Okay. So finding the area under the curve is basically finding the probability. So quickly, different properties of normal distribution. The word normal distribution is referring to a bell shape and symmetric about its mean. The normal distribution is completely defined by its mean mu and the standard deviation sigma. The total area under the curve got to be equal to 1 because that's the highest probability. Okay, so this picture looks just like the empirical rule as you've seen before. Alright, so rather than call them empirical rule, now we're going to begin to call them the normal distribution. Alright. And back in chapter 3, I believe, we talk about standardizing our normal distribution. We talk about standardizing our x-axis. Okay, make them into the z-score. So here we go again. Alright, standard normal distribution. So rather than finding the area or probability under the curve for every different problem with the different mean and standard deviation, we can just find the z-score first, and then once I convert my axis, go from the regular mean and standard deviation, standardize them into a z-axis. Okay, then I can look up values on the table or use a calculator to find the area under the curve. So when we standardize our problems, okay, the mean is always going to be 0. To the right one, to the left one will be 1 standard deviation to the right and to the left. Okay, so and I believe I actually show you something look like this back in chapter 3 before. So we are trying to standardizing from every problem, make them into one type of x-axis, so we can easily look it up our area under the curve or probability on the table or using the calculator. Alright, so as you can recall this formula, when we want to standardize the normal random variable, okay, convert them all into z-score, we take our random variable x minus the mean divided by the standard deviation. Alright, so once I standardize it, the mean right here is always going to be 0. To the right 1, to the left 1, standard deviation away. To the right 2, to the left 2, or to the right 3, or to the left 3 of the standard deviation. And we can see to the right, 1 standard deviation to the right or left, together the center was the 68% under the empirical rule. Okay, so everything is basically going back to what we learned from chapter 3. Alright, so the only difference is now when we're talking about the same normal distribution, we are actually wanting to find, okay, the area under the curve, which is going to be the probability. Okay, what's my probability under the curve? Alright, so let's refresh our memory on the z-score here. See if we remember how to standardize it. So I'm gonna copy this formula down. Oh, you know what? I'm gonna just go to the formula sheet. Alright, your standard score. This is my formula. X minus the mu divided by the standard deviation. This is not that pretty. We'll use this one instead. Alright, let's take it to the next page. Alright, so calculate your standard score. So my random variable x is at 89.7, where the mean is 88.2, and the standard deviation is 89.1. So what's happening here is normally the mean, let me see where that picture is, right here. Okay, so normally the mean, let me go back here. Normally the mean is right here in the middle, right, which is 88.2. Alright, so the 88.2 is under the regular random variable x axis. Standard deviation is 89.9. Alright, so I can go one standard deviation to the right and left, and if I go to the right one, I just add 89.4. If I go to the left one, that will be 88.2 minus, okay, 89.9. Alright, so what we want to do here is standardize this. So under the z-score, the mean is always going to be 0. Okay, so when it says calculate the standard score, that means calculate the z-score. So that means for my z-score, I will take my, so real quick, the 89.7 is about right here, right, a little bit to the right. The random variable x 89.7 is going to be slightly to the right of our mean. So if I will convert it, take my 89.7 minus the mean 88.2 and divided by the standard deviation 89.4. So what we want to do is look at this 89.7, the x, in terms of how many standard deviation away from the mean. Okay, so if I will subtract right now 89.7 minus the 88.2, this answer 1.5 means the 89.7 is 1.5 places to the right of my mean 88.2. So when we want to convert it into in terms of standard deviation, we divide it by the 89.4, and that tells me that this 89.7 is about 0.02 place to the right of the mean in terms of a standard deviation. It's about 0.02 standard deviation to the right of the mean. Okay, so for the z-score, we always round to 2 decimal place. Okay, so this same 89.7, okay, 1.5 places to the right of the 88, in terms of a standard deviation, is only going to be 0.02 place to the right of the mean. Okay, that's what it represents, standardizing, okay, your x-axis into a z-axis. We standardize it, so that means doesn't matter what kind of mean the problem has, what kind of standard deviation the problem has, we all gonna make them into a z, same axis, same z-axis. So we can talk about in terms of how many standard deviation away is that random variable. All right, so let's try another one. So my random variable x is 97.2. The mean is at 90.1. So let's say 90.1 is right about here. My random variable is 97.2, slightly to the right. Alright, standard deviation is 89.7. So if I will standardize it in terms of standard deviation, I know at the mean 90.1, the z-score will be 0. So let's see what this 97.2 will turn out equal to in terms of standard deviation. So if I take the 97.2 minus the mean, which is 90.1, divided by the standard deviation, alright, 7.1. That means this number 97.2 is 7.1 places away from the 90, the mean. In terms of standard deviation, divide both sides by 89.7, it's about 0.08 places away. Okay, so my answer, my z-score for this 97.2 is only 0.08. Okay, my graph is not very good, and I do apologize, because if you think about it though, if I will go with the empirical rule that we done before, 90.1 is the mean. One standard deviation to the right will add 89.7. So that means 179.8 is way out here, will only be one standard deviation to the right. So this 97 is actually going to be very, very close to the mean. Okay, so just like what we did back in chapter 3, okay, we convert into a z-score, and once we convert into z-score, then we will begin to talk about the area under the curve. Okay, standardizing all the problems into one same z-axis. Alright, so this is just a quick introduction. In the next lecture video, we're going to talk about how do we find the area under the curve, or how to find the probability under the curve. Alright, thank you for watching.